Good afternoon, everybody. I am Dr. Harishankar Srivastava from Indian Institute of Remote Sensing, ISRO, Dehradun. And today I am going to talk about microwave remote sensing in soil moisture studies. Uh, First of all, I would like to start my talk from the very basic definition. What is soil moisture? Actually, you can get number of definitions as far as soil moisture is concerned, but the simplest and most like well accepted definition as far as microwave is concerned is that it is the temporary storage of water within a shallow layer of the Earth's upper. Soil moisture estimation and soil moisture monitoring is very important parameter for many applications. Now the question comes, why microwave for soil moisture estimation? The first answer is, this is a direct method. Direct method means like you can attempt soil moisture estimation using optical data also, thermal data also. But then why microwave? Because optical remote sensing can also give you some idea about the soil moisture estimation, but it is relying on the reflection from the target. What does it mean? It means that if an agricultural field is moist, its reflectance will be low. So based upon the reflectance, you can get an idea about the soil moisture status of a given agricultural area. But like if I compare two cases, the first case is soil is dry but it's a black cotton soil, and the other case is soil is moist, it's a normal loamy soil and it is moist. Then in both the cases, since we are relying on the reflection, we can assign both the fields into moist category, and which is not a fact. So this optical remote sensing, and moreover optical remote sensing, the penetration depth is very poor. It means like if vegetation cover is there, it is nearly impossible to get an idea about the soil moisture below the crop cover or vegetation cover. Similarly, thermal data also we can also use thermal data, but the pixel size is coarse. So finally, the microwave remote sensing is supposed to be the best option for soil moisture estimation. So the first reason is this is a direct method, and the large difference between the dielectric constant of water that is 80, about 80, and dry soil, which is between 3 to 4 at microwave frequencies, is basically the key factor for using microwave for soil moisture estimation. As I told you that in case of optical remote sensing, due to poor penetration capability, it is not a good choice. But for microwave remote sensing, due to longer wavelengths, it can penetrate inside the soil column, as well as even in the presence of vegetation or in the presence of crop cover, we can estimate the soil moisture because microwaves can easily penetrate through crop cover or vegetation cover. And this is the formula. This penetration depth is directly proportional to wavelength, and epsilon dash is what? It is the real part of dielectric constant, and epsilon double dash is the imaginary part of dielectric constant. So it is directly proportional to wavelength, and if the dielectric constant is higher, then also we will get if the dielectric constant is higher, then the penetration depth will be less. Now I would like to make you feel that how microwaves are able to penetrate inside the target, whether it is a soil medium or vegetation. Here you can see we have collected the data at X band, C band, and L band, and you see this. You concentrate on this circle, red circle. I have marked this red circle on all the 3 images acquired at X band, C band, and L band, and here you can see there is no impression of soil moisture in this X band, in C band also, but whereas at L band image you can see this a channel which is basically a paleo channel, and it was moist below some 60-70 centimeter below the upper soil surface, and upper soil surface was perfectly dry. Upper soil surface was perfectly dry. So this here you can realize that longer wavelengths have sufficient amount of penetration depth inside a soil medium, and that is why while using longer wavelengths we can also collect soil moisture at profile level. Now here you can see as volumetric soil moisture is increasing, dielectric constant is also increasing, and this is a key factor that when volumetric soil moisture increases, dielectric constant increases, and increase in dielectric constant will result in increase in high backscatter. So in India we have started soil moisture estimation way back during late 80s. We have started soil moisture estimation and other of course other microwave related studies also, but that time we were using ground based spectrometer data, and this slide is showing our earlier results when satellite based microwave data, synthetic aperture radar data was not available. This is the map. This ERS-1 was actually the first operational SAR sensor launched in July 1991, and at ISRO also, in fact all over the world, scientists have explored and exploited this data for soil moisture estimation, and here at India at ISRO also we also have explored this ERS-1 data for soil moisture estimation. This is a map over a taluka known as Kiravli at district Agra. But one thing I would like to mention, that along with its very high sensitivity towards soil moisture, microwave signals are also sensitive for other target properties like surface roughness, crop cover, and soil texture. So although we can generate a soil moisture map with the help of single channel SAR data, but if we will not address these issues like impact of surface roughness, vegetation and cover and soil texture on soil moisture estimation using microwave, then the accuracy will be very low. This slide is showing the impact of surface roughness. You can see when the surface was very smooth, then we will get very low backscatter. Why? Because here we are observing only the backscattering portion. Backscattering means what? In fact, scattering is taking place in all the directions, but since we are using a monostatic sensor, static antenna for remote sensing purpose, so only that component of scattered energy which is coming in the backward direction, we will be able to sense that part. So if the surface is very smooth, nothing will come back and we will get very low backscatter. Now if the surface is medium rough, then most of the proportion of the NT will go in the opposite direction, but some amount of energy will come back in the backward direction. But if the surface is very rough, then scattering will take place in all the directions and sufficient amount of backscattered energy like microwave signals we will receive in the backward direction also. So it means if the surface is very smooth, we will get very low backscatter. If the surface is medium rough, we will get medium backscatter, and if the surface is very rough, we will get very high backscatter. Now this surface roughness, I told you earlier that high soil moisture also produces high backscatter, but at the same time high surface roughness also producing very high backscatter. It means like if we will not address the issue of surface roughness, it will be difficult for a user to decide that whether this high backscatter is coming due to high soil moisture or high surface roughness. This slide is showing the impact of surface roughness on SAR backscatter. You see, this set of fields, these are not only 3 fields. It is this dot is showing the plus minus standard deviation and plus sign is showing the mean. So it is the mean. This cluster is showing the mean and standard deviation of more than 100 points. Okay, so this cluster is representing smooth dry fields, whereas this cluster is representing rough dry fields. Now you see, although the soil moisture in both these cases was very low, but due to surface roughness, the difference between this point and this cluster and this cluster may be from say -6 to -14 dB. So it's a huge variation because soil moisture produces approximately some 3 to 4 dB variation. So if like see 2 to 6, so it is around some plus minus 3 dB or plus minus 4 dB. So if there is a plus minus 3 dB or plus minus 4 dB variation is due to change in surface roughness, it is impossible to estimate soil moisture in the presence of surface roughness. Now these are the common bands that we are using for soil moisture estimation. It is Ka, K, Ku, Xc, Sl and P bands. Now out of these bands, as I showed you earlier, that penetration depth is directly proportional to wavelength or lambda. It means like if I start from Ka and go towards P band, then penetration will also increase from Ka to K to Ku to X to C to L, P and so on. Now the surface roughness, actually there is a very interesting fact as far as surface roughness from microwave point of view is concerned. Surface roughness is not a fixed parameter of target as far as microwaves are concerned. It is a function of wavelength and the incidence angle. Means if we are using longer wavelengths, then surface roughness will decrease, and if I will use shorter wavelengths, then surface roughness will increase. This slide is showing a very interesting case. Here I am showing three images: X band, C band and L band. Now you concentrate on three fields I have marked as 1, 2 and 3 on all the three images. Now you see field number 1 appears bright on X band, on C band as well as on L band. What does it mean? It means that, and one more thing, all this area was dry. This data was acquired in the month of April 1994. So here you can see that if field number 1 appears rough on the three images, it means it is very rough, because normally medium rough fields will appear smooth on L band. Whereas field number 3, you see, it appears dark on all the three images. What does it mean? It means that field number 3 is representing a very smooth field. Very smooth field. Why? Because normally all the fields appear rough on X band, and if anything is appearing smooth on X band, it means it is very smooth. Now coming to this field number 2, it appears bright on X band and C band. It means and very smooth, or it is producing low backscatter on L band. Now if a field, a dry field, is producing high backscatter on X band and C band, and L band on L band, it is producing low backscatter, it means this field is medium rough. So now what I wanted to emphasize, that field 1 represents very rough field, field 3 represents very smooth field, and field 2 represents medium rough field. What does it mean? It means that if we use multi-frequency data, then we can categorize surface roughness. Okay? Here also you see this river appears broader on this image, high angle image, and thinner on low incidence angle image. Why it is so? It is because this type of area where the surface is smooth and moist, on high incidence angle this area appears dark, and that is why it mixes with the smooth water body, and water also gives low backscatter. This smooth surface also gives low backscatter, and that is why thickness of the river looks very very high. Whereas low incidence angle due to high soil moisture, low incidence angle gives high backscatter for this moist area and low backscatter for this smooth water body river, and that is why the you see here again you see this dark line and white line. White line represents moist river sand and dark line represents water. Whereas on high incidence angle, dark line or water gives low backscatter, as well as the smooth river sand is also giving low backscatter. Now what does it indicate? It again indicates that if we have multi-incidence angle data, we can again characterize surface roughness. Now this slide is showing that if we take the difference of backscattering coefficient at two incidence angles, then it is a good indicator of surface roughness. If the value is less, if the difference between sigma naught at low incidence angle and sigma naught at high incidence angle, it means surface is very rough. So this quantity sigma naught at low incidence angle minus sigma naught at high incidence angle is inversely related with surface roughness. Okay, so if I use this term as an extra term in the soil moisture retrieval model, again we can incorporate the effect of surface roughness in the soil moisture retrieval model. So it means we can go for multi-frequency data also, we can go for multi-incidence angle data also. Similarly, go for multi-polarized data also. If we take the difference between or if we take the depolarization ratio, then it is also a good indicator of surface roughness. You see in this graph plotted RMS height versus depolarization ratio, and we observe that it is giving a trend between, it is showing a cut trend between roughness and depolarization ratio. Okay, so now we have three options. Depending upon the resources, depending upon the data availability, we can opt any option. We can go for multi-incidence angle data, we can go for multi-polarized data, we can go for multi-frequency data, depending upon the resources and data availability. Here also you see, if I take co-polarization ratio, then also it is showing a relation between surface roughness. Now similarly, crop cover or vegetation cover also decreases the SAR sensitivity towards soil moisture. See, signals can come to the ground, directly interact with the ground and can go back. Now the other situation is signal can hit, then they can again hit the trunk and then they can go back. Or they can come, hit the ground, then hit the canopy and again they can go back. Or directly the signal can interact with the canopy or vegetation canopy. So in all these 5 cases, the basic physics or the interaction of SAR with the target is different, and it is really difficult to handle all these processes separately. So what we do, normally we take the overall effect of vegetation cover, and for that also methods are available. Again we can go multi-frequency data, multi-polarized data, multi-incidence angle data. Now you consider the example. See, suppose I am acquiring an image over an agricultural area. Then if the area is covered with crop and I am getting coefficient as sigma naught total, what does it mean? This sigma naught total is basically the backscattering that is coming from the crop plus the backscattering that is coming from the soil upon L square. Here L square is the loss factor. Why loss factor? Because signal has to travel twice through the vegetation canopy. Once when the signal is coming and going toward the soil, and the next time when it is going back from the soil. So this is the basic equation. This is the basic equation, and by using this equation we can estimate how much backscattering is coming from crop, how much is backscattering is coming from soil, and what is the two-way attenuation introduced by the crop canopy. Now this slide is showing that by selecting proper SAR sensor detectors, we can target a specific portion or a specific component of a target. See, here incidence angle is high, that is why we will receive the backscatter only from the crop canopy. But in this case, in the case A, since the incidence angle is low, that is why the signal is able to penetrate the vegetation and it can reach up to the, okay? Why in case B, signal is not able to reach up to the ground? Because in this case, slant height increases. Slant height of vegetation increases due to change in or increase in incidence angle. And for the case number C and D also, here we are using longer wavelengths. That is why at low incidence angle, the signal is not only able to penetrate the vegetation cover, but it is also able to penetrate inside the soil medium. But when we increase the incidence angle very high, like when we select very high incidence angle, even these longer wavelengths are not able to penetrate inside the soil medium. Okay? Now this slide is showing the effect of incidence angle. You can see as incidence angle is increasing, the sensitivity towards soil moisture is decreasing. And one more, this bright patch is due to high soil moisture. And you can see on optical image, this whole area is covered with vegetation. So this is a proof that microwave signals are highly sensitive for soil moisture even in the presence of vegetation cover. Now here again you can see that low incidence angle data due to lower slant height can reach up to the ground, whereas high incidence angle data due to high slant height of the vegetation, like it will also able to reach, but at the same time it will bring a lot of information about the vegetation cover. Now, in order to prove that which data is bringing the backscatter from which portion of the target, means here what is target? A crop covered field. So it has crop as well as underneath soil surface. Now what I have done, I have plotted soil moisture versus backscattering coefficient for these two cases, and you can see these red marks, red points are showing a definite relation between soil moisture. Means as soil moisture is increasing, these red points are also showing higher backscatter. What does it mean? That even in the presence of crop cover, high incidence angle data, microwave data is able to sense soil moisture. Whereas you see these blue points, since blue points are representing what? Backscattering coefficient acquired at high incidence angle, and due to, because they are forced to travel longer distance inside the vegetation medium. In this case, you can see that these points are not showing any relation with moisture. Then when they are not showing any relation with soil moisture, then why this spread is there? This spread is due to variation in crop condition or crop growth or crop volume, okay, or crop type. So it indicates that this high incidence angle data is basically an indicator of vegetation cover instead of
soil moisture, it is giving the information about vegetation cover. It means if I incorporate the this high backscattering coefficient in the soil moisture retrieval model as an extra term, then in that case we will be able to incorporate the effect of crop cover in the soil moisture retrieval model. Now, as far as the effect of soil texture is concerned, due to water holding capacity of different soil particles, there are three broad particles inside the soil medium: sand, silt and clay. And water holding capacity of clay is higher than sand and silt and sand. So due to change in water holding capacity, if the soil texture changes, then availability of bound water and free water also changes inside a soil medium. And this is resulted in change in backscattering also. What I mean to say, if the soil moisture of a sandy field and a field which has high clay content is same, if the soil moisture is same, even though we will get slightly lower backscatter for clay soil, because in clay soil the proportion of bound water is much higher as compared to sandy soil, and that is why like due to higher proportion of bound water, its dielectric constant will also be slightly lower, and which will result in low backscatter. So we also have to address the effect of soil texture. And what we have done, we have observed that if we represent soil moisture in terms of water above wilting point, then this quantity, this is graph number 4, you can see it is showing the maximum correlation. It is showing the maximum correlation of 0.96. So if we are representing soil moisture in terms of water above wilting point, then this quantity is able to incorporate the effect of soil texture in the soil moisture retrieval model. These are the results that we have observed. And here you can see, this is the, when we are representing soil moisture in terms of gravimetric soil moisture, then volumetric soil moisture, then soil moisture in terms of percentage of field capacity, and here we are representing soil moisture above wilting point. And this is showing the lowest spread as far as low soil moisture related points are concerned, because in this case the effect of soil texture has been minimized. Now we can also go for scattering model, radar scattering models. But these models, there is a problem with these models. We cannot apply these models over a very large area due to change in distribution of surface roughness, and moreover these models have their own applicability range. So although these models gives very good results for a area which is under controlled condition, but for a very large area, say some 10,000 square kilometer or some more than 20,000 square kilometer area, it is difficult to apply these models. Now this is a methodology which we have developed at ISRO, and here either we can use multi-incidence angle data or multipolarized data, and in both the cases we can incorporate the effect of surface roughness, crop cover and soil texture in the soil moisture retrieval model. These are the results, and the main thing, we have developed the model over different sites and validated over a different site. So model has been developed over parts of Agra, Mathura and Bharatpur districts, and it has been validated over parts of Saharanpur and Haridwar districts using the same methodology. Now these are the results of a very unique opportunity we have got here at ISRO. This data is from DLR, German DLR ESAR, experimental SAR data, and here we have got X band, C band, L band and P band. So these slides are showing the results that if I have multi-frequency data, then we can get an idea, we can have an idea about the soil moisture status inside a soil profile. Okay. one thing I would like to request all of you, because it is difficult to understand, because this slide is containing a lot of content. So for me also it is difficult to explain each and everything, and for you also it is difficult to understand each and everything from this slide. So in all my slides, I have mentioned the paper where it has been published. Most of the work that I am showing during my lecture is my own work, and most of this work is published. So everywhere I have mentioned, like for example, this work has been published. This paper, the name of this paper was How Far SAR Has Fulfilled Its Expectation for Soil Moisture Retrieval, and it has been published in Speed Digital Library. Most of this work is available online on internet. And one more thing, I would like to go back. I would like to go back to show you one important thing, because this soil moisture is a very big area. So within a small time of 1 hour, it is difficult to explain everything. So in the first slide itself, I see here I have mentioned 2 links. The first link is https iarsacademia.edu/Dr. Harishankar Srivastava papers. Okay. So when you will go, if you will go on this site, you will get number of my papers on soil moisture. There, whatever I am showing here, most of the work is published. So detail, you can go through these papers and you will be able to understand each and everything. Okay. And if you feel any problem, not today only, anytime you can send me an email. My email address is also mentioned here. And the other site is http://scholar.co.in. So these 2 addresses, these 2 links, you can, if you go to these 2 links, many of my papers you will be able to see, and then it will be very easy for you to understand whatever I am saying here. And again I would like to show, see, this slide has been taken from one of my paper. The paper, even in this case the link is also given. These papers are freely available on internet. Similarly, see, this is this I have taken from my PhD thesis. This is also available at openthesis.com. This slide has also been taken from my PhD thesis. This work has been taken, it is my own work, and it has been published in IEEE Transactions on Geoscience and Remote Sensing. So if you are not able to understand fully, because I am trying my best to explain, but within a small period time of 1 hour, it is for you also it is difficult to understand everything. So simply you, if you want, if you feel interest in this slide, you please go to this paper, you will be able to understand everything. Now this work has been published in a journal called Geocarto International. This work has been published in Current Science. There you will be able to understand that how to extract the backscattering that is coming from crop canopy and the backscattering that is coming from the underneath soil. Okay. So this is my request. If you are feeling more interest in any slide, you kindly go through those papers. Like this work has also been published. This journal you can access. Okay then. So coming to the point. Okay. This methodology we have developed here at ISRO, and here you can use either multi incidence angle data or multi-polarized data. So these results are from published papers. So you can go in detail of even a minute thing which has been mentioned here. Okay. So this slide is basically showing, I'm telling in a very broad way, this slide is showing the fact that if we have longer wavelengths and at the same time a combination of bands, low, medium and long wavelengths, then we can have an idea about the soil moisture status in the complete soil profile. This slide is showing the sensitivity of multipolarized data towards the orientation of the target. Here you see these fields are covered with pumpkin crop and these fields are covered with bajra crop. Now the basic difference between pumpkin crop and bajra crop is pumpkin crop, it has a broad leaf structure and these broad leaves are mostly horizontally oriented, parallel to the ground. Whereas in the case of bajra, this crop is vertically oriented. Okay, so you can see, you can go through these graphs, and then you will be able to realize that that if we use VV polarized data, HH polarized data, they are behaving differently with the target according to its orientation. Now, so far I told you that how to address this problem, the problem of surface roughness, crop cover and soil texture as far as the soil moisture estimation is concerned, because all these three parameters, surface roughness, crop cover and soil texture, they are behaving as a noise parameter. Okay, so the remedy is you have to have either multi-frequency data or multipolarized data or multi-incidence angle data. But one more option is there. If we use the fully polarimetric data, then by using the single data, we can separate out the contribution from soil moisture, vegetation biomass, vegetation volume, surface roughness. Okay. Here I am showing how this SAR polarimetry works. Now, what is the difference between multipolarized data and fully polarized data? See, if the target is dihedral or trihedral, there is no difference for multipolarized data. But if we have the phase information also, the phase information of the information about the relative phases of all the four polarizations, then we can have the complete knowledge about the target. This is linear polarized data, horizontal polarized, linearly vertical polarized. This is circular polarized, left circular, right circular, and this is elliptically polarized data. Now, multi-frequency observation of scattering mechanism using SAR polarimetry. This is also a published work in Current Science. Using SAR polarimetry, we can decompose the target vector, and by decomposing the target vector, we can get even a minute information about the target. These are the results that we have obtained using this fully polarimetric data as far as bare soil, soil moisture for bare soil, soil moisture underneath wheat cover, soil moisture underneath mustard cover, and surface roughness. This is also published work, and it is available on internet. This whole report is available on internet. You can go, the two links that I have showed to you, you can go to those links, and this report you will get. It's a thick report, some 80-85 pages report. You can go and see the work. Okay, using SAR hybrid polarimetry, this hybrid polarimetric data is available from our own RA-SET1 SAR. And first time in the world, we should feel proud that first time in the world, ISRO is able to launch this satellite, which is giving hybrid polarimetric data. So these are the soil moisture maps, temporal variation of soil moisture. These maps have been prepared, have been generated using hybrid polarimetric SAR data. Now, this paper is very important. I will request all of you that if anybody is really interested and seriously interested in soil moisture estimation using microwave, then please go through this paper. This is a review article paper. It is not my paper. It has been published from, I think, some Canada or somewhere. Some other group has published this paper. Advances in soil moisture retrieval from synthetic aperture and hydrological applications. This paper was published in Journal of Hydrology in 2013, and it is available. This is the link I am giving. So this paper is basically giving the summary of select advances in soil moisture retrieval. And here the authors have given a very comprehensive table, in which table they have mentioned what are the advancements that have taken place in the field of soil moisture estimation using SAR data. So these are the names of the scientists, the country, the study area, what methods they have used, and major findings. Like Davidson from Italy has observed, his observations are mentioned here. Okay, and in this paper, like in this review article, I am very happy to say that like that group who has written this paper have also recognized our Indian efforts. Like we see this paper by Srivastava et al. And the study area was Agra, Mathura and Bharatpur, India. The data set used was radar set 1. And here the findings are also mentioned. So this work they have taken from, they have acknowledged the efforts done by the scientists at ISRO. This work also they have mentioned here the how to incorporate the effect of surface roughness using multi-incidence angle data. This work was published in IEEE. This work they have acknowledged. And one more work, here the author is Srivastava et al., Agra, Mathura and Bharatpur study area, radar set 1 C-band. In this work was published in International Journal of Remote Sensing. This work also they have acknowledged, and they have like called it as a select advancement in the soil moisture estimation. In this work, we have explained how to incorporate the effect of soil texture in the soil moisture retrieval. So all these papers are given in the list that I have mentioned you in the first cover note. And these are the some selected publications that I think if you go through these papers, it will be like much easier for you to understand not only the soil moisture but other applications of soil moisture also, and about knowledge about the basic soil moisture also. So kindly, if you are interested, if you are really interested in this advanced field of microwave remote sensing, you can go through these papers. These are some of my selected publications. So if you are interested, you can go through. This is the list, and these papers are also, most of the papers are available, full papers are available on the site that on the link that I have shown on the first page itself. So that's all. Thanks a lot, and I'm waiting for your questions. Okay then. Thanks.